Take a deep breath. Settle into a comfortable position. Let your shoulders relax. In the next few hours, we're going to explore something truly remarkable together. We're going to talk about the parts of the universe we cannot see, the hidden components, the invisible architecture that holds everything together. And we're going to do this slowly, gently, at a pace that allows you to simply listen and let the ideas wash over you like waves on a distant shore. When you look up at the night sky, you see stars, thousands of them on a clear night, away from city lights, each one a brilliant point of light that has traveled across unimaginable distances to reach your eyes. These stars are beautiful. They're mesmerizing. They've inspired humanity for millennia, guiding sailors, sparking myths, and filling us with wonder. But here's something that might surprise you. Everything you can see in the night sky, all those stars, all the galaxies visible through our most powerful telescopes, all the gas clouds and planets and moons, everything that emits or reflects light in any way we can detect, all of that together makes up only about 5% of the universe. 5%. Let that sink in for a moment. 95% of everything that exists is invisible to us. Not because our eyes aren't good enough or because our telescopes need improvement, but because this missing majority doesn't interact with light in any way we can directly observe. It's there, influencing everything around it, shaping the cosmos at the largest scales, but we cannot see it. We can only observe its effects, like watching leaves move in the wind and knowing that something invisible must be pushing them. This invisible universe isn't some abstract concept or theoretical curiosity. It's real, it's fundamental, and understanding it changes everything we thought we knew about existence itself. So let's begin this journey together. Let's explore what scientists have discovered about this hidden reality, and let's do it in a way that feels peaceful, contemplative, and deeply calming. First, let's talk about the concept of seeing itself. When you see something, what's actually happening? Light, which is a form of electromagnetic radiation, bounces off an object and enters your eye. Your eye contains special cells that react to this light, sending signals to your brain, which interprets these signals as an image. This seems straightforward enough, but light only bounces off things that interact with electromagnetic forces. Most of the matter we're familiar with, like the material that makes up your body, this book, The Earth Beneath Your Feet, interacts with electromagnetism. That's why you can see it. But what if something exists that simply doesn't interact with electromagnetic forces? What if there are forms of matter or energy that pass right through light without affecting it at all? Such things would be completely invisible. No amount of technological advancement would allow us to see them directly because there would be nothing to see. No light bounces off them. No light is absorbed by them. They're transparent in the most absolute sense of the word. And yet they could still exist, still have mass, still exert gravitational influence on everything around them. This is not science fiction. This is where the evidence has led us, and the story of how we discovered this invisible universe is one of the most fascinating chapters in the history of science. It's a story of careful observation, patient analysis, and the willingness to accept that reality might be far stranger than we ever imagined. Our journey begins in the 1930s with an astronomer named Fritz Zwicky. Zwicky was studying something called the Coma Cluster, which is a large group of galaxies bound together by gravity, located about 300 million light-years from Earth. He was measuring how fast these galaxies were moving relative to each other. This might not sound particularly exciting, but the measurements revealed something astonishing. The galaxies were moving too fast. Let me explain what that means. When objects are held together by gravity, like planets orbiting a star or galaxies in a cluster, their speeds tell us something about how much mass is holding them together. The more mass there is, the stronger the gravitational pull, and the faster objects can move without flying apart. It's like swinging a ball on a string. The heavier the ball and the stronger the string, the faster you can swing it without it breaking free. Zwicky calculated how much mass the Coma cluster should contain, based on all the visible galaxies and stars he could observe. Then he measured how fast those galaxies were actually moving, and the numbers didn't match, not even close. The galaxies were moving so fast that, according to his calculations, they should have long ago escaped the cluster's gravitational pull and scattered into space. But they hadn't. They were still there, bound together, orbiting a common center. There was only one explanation that made sense. The cluster had to contain far more mass than he could see. In fact, it had to contain about 400 times more mass than all the visible matter combined. Zwicky called this invisible mass dark matter, and he published his findings. But like many revolutionary ideas, it was largely ignored for decades. The scientific community wasn't ready to accept that most of the universe might be invisible. As you listen to this, you might be feeling relaxed, perhaps drowsy. That's perfectly fine. Let the ideas flow around you. There's no urgency here, no test to pass. We're simply exploring together at a pace that feels comfortable and calm. Zwicky's observations sat in relative obscurity for about 40 years. Then, in the 1970s, an astronomer named Vera Rubin began studying individual galaxies in detail, measuring how fast stars were moving at different distances from the galactic centers. What she found reinforced Zwicky's earlier discovery and made the case for dark matter impossible to ignore. Rubin focused on spiral galaxies, beautiful pinwheel structures similar to our own Milky Way. In these galaxies, stars orbit around the center, just as planets orbit the sun. And just as planets farther from the sun move more slowly than those closer in, you would expect stars farther from a galaxy's center to move more slowly than those near the middle. This is what Newton's laws of gravity predict. This is what should happen if most of the galaxy's mass is concentrated in the bright, visible center where most of the stars are. But that's not what Rubin observed. Instead, she found that stars far from the galactic center were moving just as fast as those closer in. Some were even moving faster. The rotation curves, as astronomers call them, were flat instead of declining. This was completely unexpected. It was as if the gravitational rules that worked everywhere else in the universe suddenly didn't apply to galaxies. Except the rules did apply. The galaxies just contained more mass than anyone could see. Much more. Rubin's careful measurements showed that galaxies must be embedded in vast halos of invisible matter, extending far beyond the visible edges. This dark matter doesn't emit light, doesn't reflect light, and doesn't absorb light. But it has mass, lots of it, and that mass exerts gravitational pull, keeping the outer stars moving faster than they otherwise should. The evidence became overwhelming. Galaxy after galaxy showed the same pattern. The visible matter, all the stars and gas clouds we can see, makes up only a small fraction of a galaxy's total mass. The rest is dark matter, forming a kind of invisible scaffolding that the visible galaxy sits within. And this isn't just true for galaxies. Galaxy clusters, superclusters, the largest structures in the universe, all show the same gravitational signatures of enormous amounts of unseen mass. Now, you might be wondering, what is dark matter made of? That's one of the biggest questions in modern physics, and the honest answer is that we don't know yet. We know what it isn't, which is helpful. It's not ordinary matter made of protons, neutrons, and electrons. If it were, it would interact with light in some way, and we'd be able to see it. Scientists call ordinary matter baryonic matter, and dark matter is definitely not baryonic. So what could it be? The leading hypothesis is that dark matter consists of particles we haven't discovered yet. Particles that have mass but don't interact electromagnetically. They would pass through ordinary matter almost as if it weren't there. Right now, as you listen to these words, countless dark matter particles are likely passing through your body, through the walls around you, through the entire Earth, without interacting with a single atom. They're like ghosts, present but undetectable by ordinary means. Several candidate particles have been proposed. One possibility is something called a WIMP, which stands for Weakly Interacting Massive Particle. WIMPs would have significant mass, but interact with ordinary matter only through gravity, and possibly through the weak nuclear force, one of the fundamental forces of nature. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the rare occasion when a WIMP might interact with an atomic nucleus. So far, these experiments haven't found anything definitive, but the search continues. Another possibility is something called an axion. Axions would be much lighter than WIMPs but would exist in vast numbers, making up for their individual lightness through sheer quantity. Detecting axions requires different technology, and experiments are underway to search for them as well. There are other candidates too, each with its own theoretical basis and experimental challenges. The search for dark matter particles is one of the most exciting frontiers in physics right now. But even without knowing exactly what dark matter is made of, we can study its effects. We can map its distribution throughout the universe. We can watch how it influences the formation of galaxies and the evolution of cosmic structures. And what we've learned is remarkable. Let's talk about how the universe formed its large-scale structure. In the very early universe, shortly after the Big Bang, matter was distributed almost uniformly. Almost, but not quite. There were tiny variations in density, slight irregularities where matter was just a bit more concentrated in some places than others. These variations were incredibly small, differences of only about 1 part in 100,000, but they were enough. Gravity amplifies differences. Where matter is slightly more dense, gravity pulls more strongly, attracting nearby matter and making that region even denser. This denser region then pulls even more matter toward it. Over time, this process, which scientists call gravitational instability, turns small variations into increasingly pronounced structures. Dense regions become denser. Less dense regions become voids. Eventually, you get a cosmic web of filaments, nodes, and empty spaces, which is exactly what we observe when we look at the large-scale structure of the universe today. But here's the thing. If this structure had formed from ordinary matter alone, the process would have taken too long. The universe isn't old enough for gravity acting only on ordinary matter to have created the galaxies and galaxy clusters we see today. Ordinary matter had another problem in the early universe. It interacted strongly with radiation, with light. In the hot, dense conditions shortly after the Big Bang, photons and ordinary matter were tightly coupled together. The pressure of all that radiation pushed against the ordinary matter, preventing it from clumping together efficiently. Dark matter solved both these problems. Because dark matter doesn't interact with radiation, It wasn't affected by that pressure. It could begin clumping together immediately, following only gravity's pull. The dark matter formed structures first, creating gravitational wells that ordinary matter could later fall into. Once the universe cooled enough that ordinary matter and radiation decoupled, the ordinary matter followed the path dark matter had already laid out, falling into the gravitational wells the dark matter had created. This is why dark matter is sometimes called the gravitational scaffolding of the universe. It provided the framework upon which everything visible was built. Galaxies formed where dark matter concentrations were strongest. Stars formed from the ordinary matter that accumulated in these dark matter halos. Planets formed from the material surrounding those stars. And here we are, made of ordinary matter, living in a universe whose structure was shaped primarily by something we cannot see. If you're feeling drowsy now, that's wonderful. Let your mind drift with these concepts. Imagine the invisible framework surrounding everything, holding it all together. There's something deeply calming about this knowledge, about understanding that there's more to reality than what meets the eye, that the universe has hidden depths we're only beginning to explore. Now, let's consider what this means for our place in the cosmos. We used to think that what we could see was essentially everything that mattered. The stars, galaxies, and nebulae observable through telescopes represented the universe in its entirety. We were made of the same stuff as the stars, carbon and oxygen and nitrogen, all created in stellar furnaces. We understood matter because we could study it directly in laboratories. The universe felt knowable, accessible, made of familiar building blocks. Dark matter changes this perspective profoundly. The matter we're made of, the matter that makes up everything we can see and touch and measure directly, is a minority component of creation. We're the rare exception, not the rule. Most of the matter in the universe is fundamentally different from us, operating by different rules, invisible to our senses and instruments. Some people find this unsettling, but there's another way to look at it. The discovery of dark matter is a reminder of how much remains to be learned, how many mysteries still await us. The universe is deeper, stranger, and more complex than we thought. Rather than making us less significant, this revelation makes our existence more remarkable. We're part of something vast and mysterious, living in a cosmos that continues to surprise us, to challenge our understanding, to invite us to keep exploring. And we haven't even talked about dark energy yet. Dark matter is mysterious enough, making up about 27% of the universe's total energy content, but there's something even more abundant, even more mysterious, something that makes up about 68% of everything that exists. We call it dark energy, and it's even harder to understand than dark matter. Before we delve into dark energy, let's take a moment to appreciate where we are in this journey. We've established that the visible universe is only a small fraction of what exists. We've explored how scientists discovered dark matter through careful observation of gravitational effects. We've discussed how dark matter shaped the formation of cosmic structures. You've been listening patiently, calmly, letting these ideas settle into your awareness like snow falling on a quiet winter evening. There's no rush. We have all the time we need. The story of dark energy begins with Einstein, though he didn't realize it at the time. In 1915, Einstein published his general theory of relativity, which reimagined gravity not as a force acting at a distance, but as the curvature of space-time itself. Massive objects bend the fabric of space and time around them, and other objects follow the curves this bending creates. It's an elegant, beautiful theory that has passed every experimental test we've thrown at it. But Einstein's equations had a problem, or what Einstein thought was a problem at the time. The equations predicted that the universe should be either expanding or contracting. It couldn't just sit still. This bothered Einstein because in the 1910s and early 1920s, everyone assumed the universe was static and eternal, unchanging on the largest scales. Stars might be born and die, but the overall structure of the cosmos was thought to be permanent. To make his equations consistent with a static universe, Einstein added a term he called the cosmological constant. This was essentially a property of space itself, a kind of energy inherent in empty space that would push outward, counteracting gravity's tendency to pull everything together. With just the right value for this cosmological constant, Einstein could create a model of a universe that neither expanded nor contracted, but remained perfectly balanced. Then, in the late 1920s, Edwin Hubble made a discovery that changed everything. Hubble was observing distant galaxies, measuring their light spectra. He noticed something remarkable. The light from these galaxies was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more its light was redshifted. This redshift indicated that these galaxies were moving away from us. Moreover, more distant galaxies were moving away faster than nearby ones. There was only one straightforward explanation. The universe was expanding. Space itself was stretching, carrying galaxies apart like dots on an inflating balloon. This expansion had been happening since the Big Bang, the moment when the universe began. And if the universe was expanding, Einstein's cosmological constant wasn't necessary. Gravity alone, working against the momentum of the initial expansion, would determine the universe's fate. Einstein reportedly called the cosmological constant his biggest blunder. If he had trusted his original equations, he might have predicted the expansion of the universe before Hubble observed it. The cosmological constant seemed like an unnecessary complication, so scientists discarded it. For decades, it was essentially forgotten, a footnote in the history of cosmology. But the story wasn't over. In the 1990s, two teams of astronomers were studying distant supernovae, incredibly bright stellar explosions that can be seen across vast cosmic distances. These particular supernovae, called Type Ia supernovae, are useful because they have very consistent brightness. When you observe one, you can determine how far away it is based on how bright it appears. By measuring the light from these supernovae, astronomers can map the expansion history of the universe. Both teams expected to find that the universe's expansion was slowing down. Gravity, after all, pulls everything together. It should act as a brake on the expansion, gradually slowing it over billions of years. The question was how much it was slowing. Would it slow enough to eventually stop and reverse, leading to a big crunch? Or would it continue expanding forever, just at an ever-decreasing rate? What they found shocked everyone. The universe's expansion wasn't slowing down, it was speeding up. Distant supernovae were dimmer than expected, indicating they were farther away than they should be if the expansion rate had remained constant or decreased. Something was pushing the universe apart, accelerating its expansion against gravity's pull. This discovery earned the lead researchers the Nobel Prize in Physics in 2011. It also resurrected Einstein's cosmological constant in a new form. Whatever was causing this acceleration, it behaved very much like the energy Einstein had proposed, a property of space itself that created a repulsive effect. Scientists called this mysterious influence dark energy, and it quickly became clear that it dominates the universe. Dark energy is even more mysterious than dark matter. With dark matter, we at least have a general idea of what it might be, some form of massive particle. With dark energy, we're much less certain. Is it truly a cosmological constant, a fixed property of space that never changes? Or is it something more dynamic, a field that varies over time and space? These are questions scientists are actively investigating. One possibility is that dark energy is vacuum energy, the intrinsic energy of empty space itself. Quantum mechanics tells us that even empty space isn't truly empty. Particles and antiparticles constantly pop into and out of existence in fleeting moments, borrowing energy from the quantum vacuum and then returning it. These quantum fluctuations give empty space an energy density. Perhaps this energy is what we observe as dark energy. There's a problem with this idea, though. When physicists calculate how much vacuum energy there should be based on quantum mechanics, they get a number that's vastly larger than what we observe. Not just a little larger. About 10 to the power of 120 times larger. That's a 1 followed by 120 zeros. This is perhaps the most embarrassing discrepancy between theory and observation in all of physics. Something is very wrong with either our understanding of quantum mechanics or our understanding of gravity, or possibly both. Despite this problem, the evidence for dark energy is solid. Multiple independent observations confirm it. The supernova measurements were just the beginning. Scientists have also studied the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. The patterns in this radiation tell us about the universe's composition and geometry. They confirm that dark energy makes up about 68% of the universe's total energy content. Other evidence comes from studying the large-scale structure of the universe, the way galaxies cluster together, the way matter is distributed across cosmic scales. These patterns are influenced by dark energy. When scientists model the universe's evolution, they find that including dark energy produces results that match what we observe. Without it, the models don't work. So we're left with a profound mystery. The majority of the universe is made of something we don't understand. 27% is dark matter, invisible but at least gravitationally similar to ordinary matter. 68% is dark energy, which acts in a completely different way, pushing space apart rather than pulling it together. And only 5% is the ordinary matter that we can see and study directly, the stars and galaxies and planets that fill our telescopes and inspire our wonder. Take a moment to let this settle. Breathe slowly. Feel the weight of your body at rest. In the darkness of your closed eyes or the softness of the room around you, there's a metaphor for the universe itself. Most of it is hidden. Most of it operates beyond our direct perception, but it's there, and its effects are real and measurable. Now let's think about what the invisible universe tells us about the nature of reality itself. For most of human history, we assumed that what we could perceive directly represented the full scope of existence. If we couldn't see it, touch it, or measure it, we had no reason to believe it was real. Our senses were our guide to reality. Science has repeatedly challenged this intuition. We've discovered that air, which seems like nothing, is actually made of molecules in constant motion. We've learned that light is both a wave and a particle, that time is relative, that solid matter is mostly empty space at the atomic level. Each discovery revealed that reality is stranger than our everyday experience. Suggests the invisible universe is perhaps the most profound example of this. It tells us that our senses give us access to only a tiny slice of what exists. This doesn't mean our senses are unreliable within their domain. They evolved to help us navigate our immediate environment, and they do that job admirably. But the universe is so much larger than that immediate environment, operating at scales and in ways that our evolutionary history never prepared us for. This raises an interesting philosophical question. How do we know anything is real if we can't observe it directly? How can we be confident that dark matter and dark energy actually exist, rather than being artifacts of our incomplete theories? The answer lies in the consistency and predictive power of the models that include these invisible components. When scientists propose the existence of dark matter and dark energy, they're not just making wild guesses. They're following the evidence wherever it leads. The rotation curves of galaxies, the motions of galaxy clusters, the formation of large-scale structure, the acceleration of the universe's expansion. All of these observations point to the same conclusions. The models that include dark matter and dark energy make predictions that can be tested against new observations, and those predictions keep being confirmed. This is how science works at its best. We can't always observe things directly, but we can observe their effects. We can construct models and test them rigorously. When multiple independent lines of evidence all point in the same direction, we gain confidence that we're on the right track, even if the full picture remains unclear. The invisible universe also reminds us of the importance of humility in our quest to understand nature. Every time we think we've figured something out, the universe reveals new depths of complexity. A century ago, we didn't know that galaxies existed beyond our own Milky Way. We thought the universe was static and eternal. We had no concept of the Big Bang, no understanding of cosmic expansion, no hint of the invisible majority that shapes everything we see. Now we know better, and yet we still have so much to learn. We don't know what dark matter particles are. We don't understand the nature of dark energy. We don't know if there are other invisible components we haven't discovered yet. We don't fully understand how all these pieces fit together into a complete picture of reality, but that's exciting, not discouraging. It means there are still mysteries to unravel, questions to answer, discoveries waiting to be made. The universe continues to surprise us, and each surprise deepens our appreciation for how remarkable existence truly is. As you continue to rest, perhaps drifting towards sleep, think about the invisible forces shaping your life as well. Not in a mystical sense, but in the everyday sense of things we often overlook. The air pressure holding you in place, the gravitational pull keeping you grounded, the electromagnetic forces binding the atoms in your body together, the quantum processes occurring in every cell, maintaining the machinery of life, all invisible, all essential, all operating whether you're aware of them or not. The visible and the invisible work together to create the world you experience. The same is true for the universe at large. The stars and galaxies we see are beautiful and awe-inspiring, but they're just the visible tip of a much larger reality. The invisible scaffolding of dark matter holds those galaxies in place. The invisible energy of dark energy shapes the universe's ultimate fate. Together, they create a cosmos of stunning complexity and profound mystery. Let's explore another aspect of the invisible universe, the role of computer simulations in understanding it. Since we can't directly observe dark matter and dark energy, scientists use powerful computers to simulate how the universe would evolve under different conditions. These simulations start with the early universe, shortly after the Big Bang, and run forward in time, showing how structure forms and evolves over billions of years. In these simulations, scientists input what we know about physics, the laws of gravity, the properties of ordinary matter, and our best guesses about dark matter and dark energy. Then they let the simulation run, watching as the initial nearly uniform distribution of matter evolves into the complex web of structure we observe today. If the simulation's results match what we see in the real universe, that gives us confidence that our understanding is on the right track. These simulations have been remarkably successful. When scientists include dark matter in their models, with properties consistent with observations, the simulations produce universes that look very much like our own. Galaxies form in the right places and with the right properties. Large-scale structure develops the characteristic pattern of filaments, nodes and voids that we observe. The timing of when structures formed matches what we see when we look at distant, ancient galaxies. Without dark matter in the simulations, everything goes wrong. Structure forms too slowly or not at all. Galaxies don't look right. The large-scale patterns don't match observations. This is powerful evidence that dark matter is real and that our general understanding of its properties is correct, even if we don't know exactly what particles it's made of. Similarly, simulations that include dark energy with properties matching what we've observed through supernova studies and other measurements accurately reproduce the universe's expansion history. They show acceleration beginning at the right time and proceeding at the right rate. They help us understand how dark energy influences the formation of structure on the largest scales. These simulations also let us explore what-if scenarios. What would the universe look like if dark matter had different properties? What if dark energy were stronger or weaker? What if it changed over time? By comparing these alternative universes to our own, we can constrain the possible properties of these invisible components and gain insights into their nature. One fascinating result from these simulations is the understanding of how dark matter halos form and evolve. Remember, galaxies like our Milky Way sit within vast halos of dark matter that extend far beyond the visible edges of the galaxy. These halos aren't smooth and uniform. They have structure, with denser regions and less dense regions. They can merge together when galaxies collide. They're dynamic, evolving systems in their own right. Simulations show that dark matter halos have a characteristic density profile. They're densest at the center and gradually become less dense farther out, following a specific mathematical pattern. This prediction from simulations has been tested against observations of real galaxies, and it matches remarkably well. It's another piece of evidence that our understanding of dark matter is fundamentally correct. The simulations also reveal something interesting about the relationship between dark matter and ordinary matter. While dark matter provides the gravitational scaffolding, ordinary matter plays its own important role. As ordinary matter falls into dark matter halos and forms stars, those stars create energy through nuclear fusion. This energy heats the surrounding gas, sometimes driving it out of the galaxy entirely in powerful winds. This process, called feedback, affects how galaxies grow and evolve. The interplay between dark matter and ordinary matter is complex and fascinating. Dark matter creates the environment where galaxies can form, but ordinary matter, through the formation of stars and the energy they produce, influences the final properties of those galaxies. Understanding this interplay is crucial for understanding why galaxies look the way they do. Let's talk about one more aspect of the invisible universe that's particularly intriguing: gravitational lensing. This is one of the few ways we can actually see dark matter, or at least see its effects directly and dramatically. Einstein's general relativity tells us that massive objects bend space-time around them. Light, traveling through this bent space-time, follows curved paths. This means that a massive object can act like a lens, bending light from more distant objects and creating distorted or magnified images. This effect, called gravitational lensing, was first observed during a solar eclipse in 1919, when stars near the sun's edge appeared slightly shifted from their usual positions. The sun's gravity had bent their light, just as Einstein predicted. This observation made Einstein famous worldwide and confirmed general relativity in a dramatic way. But gravitational lensing isn't just a curiosity. It's a powerful tool for studying the universe, including its invisible components. When light from a distant galaxy passes through a massive galaxy cluster on its way to us, the cluster's gravity bends and distorts that light. We see multiple images of the background galaxy, stretched into arcs or even complete rings around the cluster. By carefully analyzing these distorted images, scientists can map out the distribution of mass in the lensing cluster. This includes all the mass, both visible and invisible. When they do this, they find that the total mass is much greater than the visible mass. Moreover, the distribution of this total mass doesn't match the distribution of visible matter. The invisible mass, the dark matter, has its own distribution, sometimes centered on concentrations of visible galaxies, sometimes offset from them. In some cases, gravitational lensing has revealed dark matter structures that contain very little visible matter at all. These are called dark matter clumps or dark halos, and their existence is exactly what dark matter theory predicts. Not all dark matter is associated with bright galaxies. Some of it exists in concentrations that never attracted enough ordinary matter to form significant numbers of stars. Gravitational lensing gives us a way to map dark matter directly, without relying solely on its gravitational effects on visible matter's motion. It's a powerful validation of the dark matter concept and provides detailed information about how dark matter is distributed throughout the universe. One particularly famous example of gravitational lensing revealing dark matter comes from a system called the Bullet Cluster. This is actually two galaxy clusters that collided and passed through each other. When scientists observed the aftermath, they found something remarkable. The visible matter in the clusters, mostly hot gas that emits X-rays, had interacted during the collision and been slowed down. It concentrated in the region between the two clusters where the collision occurred. But when scientists used gravitational lensing to map the total mass distribution, they found that most of the mass was not in the center where the gas was. Instead, it was still with the galaxies themselves, which had passed through the collision relatively unscathed. This makes perfect sense if most of the mass is dark matter. The dark matter doesn't interact with itself strongly, so the dark matter halos from the two clusters passed right through each other, barely affected by the collision. The dark matter stayed with the galaxies, while the ordinary matter in the form of hot gas got hung up in the middle. The Bullet Cluster is sometimes called the best evidence for dark matter because it shows the spatial separation between where most of the mass is, revealed by lensing, and where most of the visible matter is, revealed by X-ray observations. It's hard to explain this observation without invoking dark matter as a separate component that behaves differently from ordinary matter. As we continue this gentle exploration, let your thoughts drift where they will. Perhaps you're imagining vast halos of invisible matter surrounding galaxies like cocoons. Perhaps you're thinking about the empty space between stars, not empty at all, but filled with dark matter particles streaming past at enormous speeds. Perhaps you're simply enjoying the calm rhythm of these words, the steady flow of ideas that requires no effort, no concentration, just passive awareness. The invisible universe also raises questions about the future. If dark energy continues to accelerate the universe's expansion, what happens in the long term? The answer is both fascinating and a little melancholy. As the universe expands faster and faster, galaxies that are currently visible to us will eventually move so far away that their light can no longer reach us. The observable universe will shrink, not because anything is physically moving closer, but because the space between us and distant galaxies is stretching faster than light can cross it. Eventually, billions of years in the future, observers in our galaxy will only be able to see our local group of galaxies. Everything else will have receded beyond the cosmic horizon. This doesn't mean those distant galaxies will cease to exist. They'll still be out there, presumably evolving and existing as they always have, but they'll be causally disconnected from us. No information, no light, no signal of any kind will be able to travel between us and them. For all practical purposes, they'll be in a separate universe. Meanwhile, the galaxies in our local group, bound together by gravity, will remain visible. In fact, the Milky Way and Andromeda galaxies are already on a collision course. In about 4 billion years, they'll merge to form a larger elliptical galaxy. Future observers, if any exist, will live in this merged galaxy, seeing only the local group around them and nothing beyond. But even this won't last forever. As the universe continues to expand and age, stars will exhaust their fuel. New stars will form more and more slowly as gas reserves are depleted. Eventually, star formation will cease entirely. The universe will enter an era dominated by the slowly cooling remnants of dead stars, white dwarfs, neutron stars, and black holes. On even longer timescales, these remnants will themselves decay. Protons, once thought to be eternal, may actually be unstable, with an unimaginably long half-life. If so, even white dwarfs will eventually evaporate into radiation. Black holes will slowly evaporate through Hawking radiation, a quantum process that allows them to leak energy over enormous timescales. In the end, if dark energy remains constant, the universe will become a cold, dark, increasingly empty expanse. Matter will be dispersed so thinly that particles might travel for trillions of years without encountering anything else. The universe will approach a state of maximum entropy, where nothing interesting can happen anymore, because there's no concentrated energy left to drive change. This is sometimes called the heat death of the universe, though cold death might be more accurate. It's a future almost incomprehensibly far away so far that contemplating it requires numbers that barely mean anything to our human minds. But it's the apparent logical endpoint of a universe dominated by dark energy. There's something strangely peaceful about this far future. All the struggles, all the dramas, all the complexity of life and stars and galaxies, all of it temporary, all of it a brief flourishing in the long arc of cosmic time. It puts our own small concerns into perspective. If the universe itself is finite and temporary, if even galaxies and stars are ephemeral on the largest timescales, then perhaps we can find a kind of peace in the present moment, in the experience of existing now, in this particular configuration of matter and energy that can think and feel and wonder. Of course, all these predictions depend on dark energy behaving the way we currently think it does. If dark energy changes over time, If its strength increases or decreases, the future could look very different. Some theories suggest that dark energy could strengthen, leading to a big rip, where eventually even atoms are torn apart by the accelerating expansion. Other theories suggest it could weaken or even reverse, perhaps leading to a big crunch after all. We simply don't know. The nature of dark energy is one of the deepest mysteries in physics, and until we understand it better, all predictions about the far future remain speculative. But that's part of what makes this field so exciting. We're living in an era of discovery, a time when fundamental questions about the universe's composition and fate are being actively investigated. Let's return to dark matter for a moment and consider some of the ongoing efforts to detect it directly. Around the world, multiple experiments are trying to catch dark matter particles in the act of interacting with ordinary matter. These experiments are marvels of engineering and physics, designed to detect incredibly rare events against backgrounds of countless other particles and interactions that could mimic a dark matter signal. Most of these detectors are located deep underground, sometimes in old mines or specially constructed caverns. The rock overhead shields them from cosmic rays, high-energy particles from space that constantly bombard Earth's surface. Cosmic rays would create too much background noise, making it impossible to spot the faint signal of a dark matter interaction. The detectors themselves vary in design, but many use large volumes of ultra-pure materials like xenon or argon in liquid form. The idea is that if a dark matter particle happens to collide with a nucleus in the detector, it will cause that nucleus to recoil, creating a tiny flash of light or a small electrical signal. By carefully monitoring these detectors for any sign of nuclear recoils that can't be explained by known particles, scientists hope to catch dark matter in the act. It's an incredibly challenging task. If dark matter interacts with ordinary matter, as rarely as theories suggest, you might need to wait months or even years to see a single event, even with detectors containing tons of material. And even then, you need to be absolutely certain that what you've detected is really dark matter and not some mundane background event that slipped through your shielding. So far, these direct detection experiments haven't definitively found dark matter. There have been a few tantalizing hints over the years, signals that might have been dark matter, but could also be explained by background processes. Each time, more sensitive experiments have been built to follow up, and so far, the signals haven't been confirmed. This doesn't mean dark matter doesn't exist. It might just mean that it interacts even more weakly than we thought, making it even harder to detect. Or perhaps dark matter particles are lighter or heavier than the mass range these experiments are most sensitive to. The experiments are constantly being improved, made more sensitive, expanded to search for different types of particles with different properties. There's also another approach. Instead of trying to detect dark matter on Earth, look for it in space. If dark matter particles occasionally collide with each other, they might annihilate and produce ordinary particles that we can detect. Scientists are searching for these annihilation products using space-based telescopes and particle detectors. For example, some satellites look for excess gamma rays or positrons, antimatter electrons, coming from regions where dark matter should be concentrated, like the center of our galaxy or nearby dwarf galaxies. A few anomalies have been observed, excesses of particles that might be explained by dark matter annihilation. But as with the direct detection experiments, these signals could also have more mundane explanations. The search continues. There's something profound about these searches. Thousands of scientists around the world are dedicating their careers to detecting something that might pass through the entire Earth without leaving a trace. They're building detectors of incredible sensitivity, analyzing data with meticulous care, all in pursuit of understanding what most of the universe is made of. It's one of the great scientific quests of our time. And regardless of whether dark matter particles are detected soon or take decades more to find, the search itself advances our knowledge. Each null result tells us something about what dark matter isn't, narrowing down the possibilities. The technologies developed for these experiments often find applications elsewhere. And the spirit of exploration, the willingness to pursue difficult questions without guaranteed success, exemplifies the best of human curiosity. As you listen to these words, you're participating in this story in your own way. By learning about the invisible universe, by contemplating these mysteries, you're engaging with questions that humanity has only recently been able to ask. A century ago, no one knew these puzzles existed. Now, we're actively working to solve them. And who knows? Perhaps in another century, dark matter and dark energy will be as well understood as ordinary matter is today, and new mysteries will have taken their place. Let's think about the invisible universe from a different angle. What does it tell us about the limitations of our knowledge and the methods we use to understand reality? Throughout history, humans have often assumed that what we can observe directly represents the full scope of existence. This has been proven wrong again and again. Ancient peoples thought the earth was flat because it appeared flat to their eyes. They thought the sky was a solid dome because that's what it looked like. They thought stars were small lights affixed to this dome, not distant suns like our own. Each of these intuitions, based on direct observation, was incorrect. As our tools improved, our understanding expanded. Telescopes revealed that the universe was far larger than anyone had imagined. Microscopes showed that life existed at scales invisible to the naked eye. Particle accelerators demonstrated that matter had substructure, that atoms could be split, that even protons and neutrons were made of smaller components called quarks. Each expansion of our observational capabilities revealed new layers of reality. And yet, there was always an assumption that if we could just build better instruments, we could eventually see everything there was to see. The invisible universe challenges even this assumption. Some things might be fundamentally invisible in the sense that they don't interact with light or other forms of radiation we can detect directly. No amount of technological advancement will let us see dark matter in the conventional sense, but we can still study it. We can observe its gravitational effects. We can map its distribution through gravitational lensing. We can detect the particles it's made of if we build the right kind of detector. The methods might be indirect, but they're no less valid for that. This is actually common in science. We can't see atoms directly, but we know they exist because of how matter behaves. We can't see electrons orbiting nuclei like planets around the sun, and in fact that's not even how electrons behave, but we can observe the effects of electron transitions between energy levels. We can't see quarks in isolation, but we can see the jets of particles they produce in high energy. Collisions. Science is full of inferences from effects to causes, from visible consequences to invisible mechanisms. The invisible universe is just a particularly dramatic example of this. It reminds us that reality isn't limited to what we can perceive directly. It exists independently of our ability to observe it, and it's our job as curious beings to figure out what's really out there, even when it hides from our senses. This has implications for how we think about other mysteries too. If 95% of the universe can be invisible, what else might we be missing? Are there other components we haven't discovered yet? Other forces or fields or particles that leave only the subtlest traces? Most physicists would say yes, there probably are more discoveries waiting. Dark matter and dark energy are the two biggest mysteries right now, but they're not the only ones. We don't understand how to reconcile quantum mechanics with general relativity. We don't know why the universe has the particular fundamental constants it does. We don't know if the Big Bang was truly the beginning or if something preceded it. We don't know if our universe is the only one or if there are others beyond our observation. Each of these questions might require new observations, new theories, new ways of thinking about reality, and some of them might remain mysteries for a very long time. That's okay. Mystery is what drives science forward. It's what makes the quest worthwhile. If we already knew everything, there would be nothing left to discover. The invisible universe invites us to be humble about our knowledge while being confident in our methods. We don't know what dark matter is, but we know it's real. We don't understand dark energy, but we know it's accelerating the universe's expansion. We can admit uncertainty while still affirming what the evidence tells us. This is the essence of scientific thinking. Following the evidence wherever it leads, updating our beliefs when new evidence emerges, remaining open to surprises while maintaining standards for what counts as good evidence. Let your mind rest with these thoughts. There's no pressure to memorize anything, no test to pass. Just let the ideas wash over you like gentle waves. The universe is vast, mysterious, and mostly invisible. And yet through patient observation and careful reasoning, we can understand it better than our ancestors ever dreamed possible. We can map the invisible scaffolding that holds galaxies together. We can track the invisible energy that's pushing the universe apart. We can build a picture of reality that includes so much more than what our eyes can see. This is the power of science, and it's the power of human curiosity. We're not content to accept the world as it appears. We want to know what's really happening, even when it's hidden. We want to understand the mechanisms behind the phenomena, the causes behind the effects. And we've developed methods that actually work, that let us probe deeper and deeper into nature's secrets. The story of the invisible universe is still being written. New observations are being made. New theories are being proposed and tested. Perhaps in your lifetime, dark matter particles will be detected directly. Perhaps dark energy's nature will be revealed. Perhaps entirely new components of the universe will be discovered, things we haven't even imagined yet. Or perhaps some of these mysteries will persist for generations. Perhaps they're harder to solve than we currently think. Either way, the quest continues, and each step forward, even each dead end that rules out an incorrect theory, brings us closer to understanding the cosmos we inhabit. Now let's consider the philosophical implications of living in a universe that's mostly invisible. Throughout human history, people have grappled with the relationship between appearance and reality, between what seems to be true and what actually is true. Plato's famous allegory of the cave imagined people who saw only shadows on a wall, mistaking those shadows for reality itself. When one of them escaped and saw the real objects casting the shadows, the true reality beyond the cave, it changed everything. The invisible universe is a bit like this. We're seeing only a small fraction of what exists, the luminous matter that emits or reflects light. The majority is hidden, detectable only through its gravitational effects. We're living in a universe where appearance and reality are dramatically different, where what we see is literally only 5% of the story. This has always been true, of course. It's not as if dark matter and dark energy suddenly appeared when we discovered them. They've been there all along, shaping the universe's evolution for billions of years, creating the conditions that allowed galaxies and stars and planets and ultimately life to exist. We just didn't know about them. In a sense, every generation lives in an incomplete picture of reality, limited by the knowledge and tools available at the time. Medieval scholars had no concept of cells or DNA, of the electromagnetic spectrum, of nuclear forces. They lived in a universe that seemed much simpler than it actually was. Future generations will no doubt look back at our current understanding and see gaps and errors that seem obvious in hindsight, but are invisible to us now. This is humbling, but it's also exciting. It means there's always more to discover, always deeper questions to ask. The universe is inexhaustible in its complexity. No matter how much we learn, there will always be mysteries remaining, new frontiers to explore. The invisible universe also raises questions about our place in the cosmos. We're made of ordinary matter, the rare 5%. Does that make us special? Unusual? Or just part of the diversity of creation? In one sense, we're incredibly fortunate. If the universe were made entirely of dark matter, with no ordinary matter at all, there would be no stars, no planets, no life. Ordinary matter's ability to interact electromagnetically is what allows it to clump together efficiently, to cool down and condense, to form the complex structures we see around us. Dark matter can only form diffuse halos. It can't make anything interesting on its own, so perhaps it's appropriate that we're made of the minority component. The minority component is where all the interesting stuff happens. It's where complexity can arise, where chemistry becomes possible, where life can emerge. Dark matter provides the scaffolding, but ordinary matter is where the action is. On the other hand, there's something humbling about recognizing that most of the universe is fundamentally different from us, operating by rules we barely understand. We're not the template for reality. We're a special case, a particular manifestation of matter that can think and feel and wonder about its place in the cosmos. Both perspectives are valid. We're both ordinary and extraordinary, common and unique depending on how you look at it. This is the human condition, living in a universe vast beyond comprehension, made of tiny atoms that somehow organize themselves into beings capable of studying the cosmos itself. Take a deep breath. Let yourself relax even more deeply. Perhaps your eyes are heavy. Perhaps your body feels weightless. The invisible universe surrounds you, passing through you, shaping everything about your existence without you ever noticing. Dark matter particles streaming through your body at this very moment. Dark energy pushing space apart at scales far beyond your perception. All invisible, all essential, all part of the grand tapestry of existence. There's a strange poetry to this. You're more than what you seem, not in a mystical sense, but in a physical one. You're made of atoms forged in the cores of ancient stars. You're held together by electromagnetic forces. You're influenced by gravitational fields stretching across the universe. You're part of a cosmos that's 95% invisible, 5% visible, and 100% mysterious. Before we move on to the next chapter, let's summarize what we've explored. We've seen how scientists discovered that most of the universe is invisible through observations of galaxy rotation curves, galaxy cluster dynamics, and gravitational lensing. We've learned about dark matter, the mysterious substance that makes up 27% of the universe and provides the gravitational scaffolding for structure formation. We've discussed dark energy, even more mysterious, making up 68% of the universe and causing its expansion to accelerate. We've talked about the search for dark matter particles, the experiments trying to detect them directly, and the computer simulations that help us understand how these invisible components shape cosmic evolution. We've considered the philosophical implications of living in a universe where most of reality is hidden from direct observation. And we've reflected on what this tells us about the nature of science, the limits of our knowledge, and the ongoing quest to understand the cosmos. This is just the beginning. There's so much more to explore, so many more aspects of the invisible universe to consider. In the next chapter, we'll go even deeper, looking at the early universe, the formation of the first structures, and how dark matter and dark energy have shaped every stage of cosmic history. We'll explore the cosmic microwave background and what it tells us about the universe's composition. We'll consider alternative theories and why dark matter and dark energy remain the best explanations for what we observe. But for now, rest. Let these ideas settle into your consciousness. There's no hurry. The universe has been unfolding for nearly 14 billion years. It will continue long after we're gone. In the grand scheme of things, this moment right now is just a blink. But it's your blink, your moment to exist, to learn, to wonder, to be part of something so much larger than yourself. The invisible universe isn't somewhere else. It's here now, all around you and passing through you. It's been here since the beginning, and it will be here long after the last stars fade. You're floating in it, swimming through it, made of it in ways you're only beginning to understand, and that's beautiful. That's wonderful. That's the universe revealing itself to those curious enough to look beyond what their eyes can see. Welcome back. Take a moment to settle in once more. Feel the weight of your body, the rhythm of your breathing. Let your muscles soften. In this chapter, we're going to travel through time, exploring how the invisible universe has shaped the cosmos from its earliest moments to the present day. We'll move slowly, gently, allowing each era to unfold at its own pace. There's no rush. Time itself, as we'll see, is stranger and more flexible than our everyday experience suggests. Let's begin at the beginning, or as close to it as we can get. The Big Bang. This moment, approximately 13.8 billion years ago, marks the origin of everything we can observe. Space, time, matter, energy, all of it emerged from an incredibly hot, incredibly dense state. But let's be clear about what the Big Bang was and wasn't. The Big Bang wasn't an explosion in space. It was an expansion of space itself. Imagine the entire universe compressed into a volume smaller than an atom, then expanding rapidly in all directions at once. Not expanding into anything, because there was no outside for it to expand into. Space itself was growing, carrying matter and energy along with it. In those first moments, the universe was so hot and dense that matter as we know it couldn't exist. Temperatures were trillions of degrees. Particles and antiparticles popped into and out of existence constantly. The fundamental forces of nature, which today seem so different from each other, might have been unified into a single force. It was a realm where quantum mechanics and gravity both operated at full strength, a regime we still don't fully understand because we lack a complete theory of quantum gravity. But let's not worry about those first incomprehensibly brief moments. Let's fast forward to a time we can describe with more confidence. About 1 second after the Big Bang, the universe had cooled enough for protons and neutrons to form. These are the building blocks of atomic nuclei, made of quarks bound together by the strong nuclear force. At this point, the universe was still incredibly hot, about 10 billion degrees hotter than the core of the Sun, but it was cool enough for these particles to exist stably. Over the next few minutes, some of these protons and neutrons fused together to form the nuclei of the lightest elements: hydrogen, helium, and tiny traces of lithium and beryllium. This process, called Big Bang nucleosynthesis, lasted only about 17 minutes. When it was done, the universe consisted of roughly 75% hydrogen nuclei and 25% helium nuclei by mass, with just traces of other elements. This is the primordial composition of ordinary matter, and it matches beautifully with what we observe in the oldest stars and gas clouds today. But wait, where was dark matter during all this? Good question. Dark matter doesn't participate in the nuclear processes that created these light elements. It doesn't interact via the strong nuclear force or the electromagnetic force. So while ordinary matter was being forged into hydrogen and helium, dark matter was simply there, existing alongside it, already beginning to clump together under gravity's influence. At this early time, dark matter had a head start on structure formation. Ordinary matter was still tightly coupled to radiation, to photons. The universe was filled with incredibly energetic light, and this light exerted pressure on the ordinary matter, preventing it from clumping together. Imagine trying to build a sandcastle while someone sprays it with a high-pressure water hose. The pressure keeps pushing the sand apart. That's what radiation pressure did to ordinary matter in the early universe. Dark matter didn't have this problem. Photons passed right through it. No electromagnetic interaction means no radiation pressure. So dark matter could begin responding to gravity immediately, with slight overdensities, attracting more dark matter, starting the process of structure formation long before ordinary matter could join in. As you listen, let yourself relax even more deeply. Imagine floating in a warm bath or lying on soft grass under a clear sky. The story we're telling spans billions of years, but there's no need to rush. Each moment, each era unfolds in its own time. Just as the universe has been patient in its evolution, we can be patient in understanding it. For about 380,000 years, the universe remained opaque. It was filled with a hot plasma of electrons, protons, helium nuclei, and photons, all interacting intensely. Light couldn't travel far before being scattered by a free electron. If you had been there, you wouldn't have been able to see anything more than a glowing fog in all directions. The universe was like the inside of a star, bright and hot and completely opaque. But the universe was expanding, and as it expanded, it cooled. Temperature is related to density and volume. As space stretched, the energy density decreased and temperatures dropped. After about 380,000 years, the universe had cooled to roughly 3,000 degrees Kelvin, similar to the surface temperature of a red dwarf star. At this temperature, something crucial happened. Electrons and nuclei could finally combine to form neutral atoms. This process is called recombination, though that's a slightly misleading name since the electrons and nuclei had never been combined before. Once atoms formed, the photons that had been constantly scattering off free electrons were suddenly free to travel. The universe became transparent. This moment is one of the most important in cosmic history. The light that was released at recombination has been traveling through space ever since. As the universe expanded, this light was stretched along with space itself, shifting from visible and infrared light to microwave wavelengths. Today, we detect this ancient light as the cosmic microwave background, or CMB, a faint glow that comes from every direction in the sky. The cosmic microwave background is one of the most important pieces of evidence we have about the early universe. It's a snapshot of what the universe looked like when it was only 380,000 years old. When we study this radiation carefully, we can see tiny variations in temperature, differences of only about 1 part in 100,000. These tiny variations are the seeds of all structure that would later form. Slightly hotter regions were slightly denser. Slightly cooler regions were slightly less dense. Let's think about what these variations tell us. If the universe contained only ordinary matter, these density variations would have had a particular pattern, a particular set of frequencies or scales at which they appeared. The radiation pressure acting on ordinary matter before recombination would have created sound waves in the plasma, oscillations that would leave a distinctive imprint on the CMB. When scientists carefully measured the CMB using satellites like COBE, WMAP, and Planck, they found exactly these oscillations. The pattern matched the predictions of Big Bang cosmology beautifully. But here's the crucial point. The pattern only made sense if the universe contained both ordinary matter and dark matter in specific proportions. The dark matter affected the pattern because it provided extra gravitational pull, helping ordinary matter fall into potential wells more quickly than it otherwise would. But because dark matter doesn't interact with photons, it didn't participate in the sound wave oscillations. This created a distinctive signature in the CMB pattern, a signature that can only be explained if dark matter exists and makes up about 5 times more mass than ordinary matter. This is independent evidence for dark matter, separate from galaxy rotation curves or gravitational lensing. The CMB observations tell us not just that dark matter exists, but approximately how much of it there is. When scientists analyze the CMB data, they can determine the universe's composition. About 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers come directly from the patterns in the ancient light. The CMB also tells us about dark energy, though more subtly. The large-scale geometry of the universe, which affects how the CMB variations appear at different angular scales, depends on the total energy density. When scientists combine CMB observations with other measurements, like the distances to distant supernovae, they can determine that dark energy dominates the universe's total energy budget. So this faint glow of microwave radiation, this afterglow of the Big Bang, contains an enormous amount of information. It's a treasure trove of data about the universe's composition, age, geometry, and history. It's one of the reasons we can speak with such confidence about dark matter and dark energy, even though we don't yet understand their fundamental nature. The evidence is written in the sky, in light that has been traveling for more than 13 billion years. Now let's move forward in time. After recombination, the universe entered a period sometimes called the Dark Ages, not because anything sinister was happening, but because there were no sources of light. The CMB photons were fading as they redshifted, and stars hadn't formed yet. If you could have been there, you would have been surrounded by darkness, with only the fading glow of the CMB providing any illumination at all. But this was a period of crucial activity in the dark matter. The density variations that had been growing were now able to pull ordinary matter along with them. Remember, before recombination, radiation pressure had prevented ordinary matter from clumping efficiently. Now that obstacle was gone. Ordinary matter could fall into the gravitational wells created by dark matter concentrations. This process happened slowly at first. Gravity is a relatively weak force, and the density variations were small. But over millions of years, regions that were slightly denser grew denser still, pulling in more matter from their surroundings. These growing concentrations eventually became dense enough to form the first stars. The first stars were different from the Sun and other stars we see today. They were made entirely of primordial material, hydrogen and helium, with almost no heavier elements. This composition allowed them to grow much larger than modern stars. Some of these first stars might have been hundreds of times more massive than the Sun, incredibly bright and hot, burning through their fuel in just a few million years before exploding as supernovae. These explosions served a crucial purpose. They created and dispersed the first heavy elements like carbon, oxygen, nitrogen, iron, all the stuff that planets and life are made of. These elements were forged in the star's cores through nuclear fusion and in the intense heat and pressure of the supernova explosions. When the stars died, they scattered these elements into space, enriching the surrounding gas. The first stars also did something else important. They began to reionize the universe. Their intense ultraviolet light had enough energy to strip electrons from hydrogen atoms, turning the universe back into a plasma. This period, called the Epoch of Reionization, gradually transformed the universe from neutral back to ionized over several 100 million years. By the time it was done, roughly 1 billion years after the Big Bang, the universe had changed fundamentally. It was no longer dark and neutral, but bright with starlight and filled with ionized gas. All of this happened within dark matter halos. The first stars formed in the densest regions of the dark matter distribution. The first galaxies assembled where multiple dark matter halos merged together. Dark matter provided the scaffolding, the gravitational framework, within which all the visible drama unfolded. Without dark matter, structure formation would have taken much longer, perhaps too long for stars and galaxies to have formed at all by now. Let your breathing slow and deepen. Perhaps you notice the quiet around you, the stillness. In that stillness, imagine the universe unfolding, stars igniting in the darkness, galaxies beginning to take shape, all held together by invisible threads of dark matter. It's a peaceful image. Despite the violent stellar explosions and intense energies involved, on cosmic scales, everything moves slowly, gracefully, following the patient pull of gravity. As more time passed, galaxies grew larger through mergers and accretion. Smaller galaxies combined to form larger ones. Gas continued to flow into dark matter halos, providing fuel for new generations of stars. With each generation, the universe became more enriched with heavy elements. These elements changed everything. They allowed gas to cool more efficiently, enabling smaller stars to form, stars like our Sun. They allowed dust to form, which blocked light in certain ways and altered the appearance of galaxies. They made planets possible and eventually life. The story of galaxy formation is intimately connected to the story of dark matter. Simulations show that galaxies don't form in isolation. They form along filaments in the cosmic web, the large-scale structure we talked about in the previous chapter. These filaments are like highways of matter, both dark and ordinary, connecting dense nodes where galaxy clusters form. The entire structure resembles a three-dimensional spider web, with galaxies strung along the strands and clusters sitting at the intersections. This cosmic web is a natural consequence of gravity amplifying initial density variations. Where matter is slightly denser, it pulls in more matter, becoming denser still. But this process doesn't create spherical blobs. It creates sheets and filaments, because gravity acts most strongly along certain directions, depending on the shape of the initial density variation. The result is a universe with a characteristic pattern, filaments of galaxies surrounding vast voids that contain very little matter. This pattern has been mapped extensively through galaxy surveys. Astronomers have measured the positions of millions of galaxies, creating three-dimensional maps of the universe's structure. These maps show the cosmic web clearly. They also show that the distribution of galaxies matches what simulations predict when dark matter is included. Once again, independent evidence for dark matter's existence and properties. Now let's talk about how dark energy enters the picture. In the early universe, for the first several billion years after the Big Bang, dark energy played a relatively minor role. The universe was denser then, and gravity dominated. Dark energy's repulsive effect, whatever causes it, depends on the density of dark energy, which appears to remain constant even as the universe expands. Gravity, on the other hand, weakens as matter spreads out over larger volumes. So, in the early universe, when matter was more concentrated, gravity was stronger relative to dark energy. The expansion of the universe was slowing down, just as you'd expect if gravity was pulling everything together. But as the universe expanded and matter became more diffuse, gravity's restraining influence weakened. Meanwhile, dark energy's influence remained constant per unit volume, and there was more and more volume as space expanded. Eventually, about 6 billion years ago, dark energy became dominant. This is when the universe's expansion began to accelerate. Before this transition, the expansion was decelerating. After it, acceleration. This transition is visible in the supernova data that first revealed dark energy's existence. Distant supernovae from when the universe was younger are actually slightly closer than they would be if the expansion had continued decelerating, showing that something began pushing space apart faster. This transition has profound implications. It means the universe's fate changed. If gravity had remained dominant, the expansion might eventually have stopped and reversed, leading to a big crunch. Or it might have continued forever but gradually slowing. Instead, with dark energy dominant, the expansion will continue accelerating forever, leading to the cold, dark future we discussed in the previous chapter. The transition also affected structure formation. As dark energy came to dominate, it began suppressing the growth of new structures. Galaxy clusters that were already bound together by gravity could continue evolving, but the formation of new clusters became less likely. The largest structures in the universe froze out, no longer growing significantly. On smaller scales, like individual galaxies, gravity can still overcome dark energy's influence, so galaxies can continue to merge and evolve. But the universe's largest features are essentially set. Let yourself drift with these ideas. Imagine the universe as a vast canvas painted over billions of years with structures shaped by invisible hands. Dark matter providing the framework, gravity pulling matter together, dark energy gradually asserting itself and changing the rules. It's a story of competing influences, of forces in tension, creating the cosmos we observe today. Our own galaxy, the Milky Way, is a product of this history. It formed gradually over billions of years through countless mergers of smaller galaxies and ongoing accretion of gas. The Milky Way sits within a dark matter halo that extends far beyond the visible edge of the galaxy, perhaps 10 times farther. Most of the Milky Way's mass is in this dark halo, not in the stars and gas we can see. This dark matter halo isn't smooth. It has substructure, clumps and streams of dark matter that represent the remnants of smaller halos that merged with the Milky Way's halo over time. Some of these streams might be associated with small dwarf galaxies that are currently being torn apart by the Milky Way's gravity. The stars in these dwarf galaxies form visible streams, and the dark matter that was associated with them forms corresponding invisible streams. Detecting these dark matter streams is a goal of some direct detection experiments. If Earth happens to pass through a stream, there might be a higher flux of dark matter particles than usual, potentially making detection easier. It's a long shot, but the search for dark matter requires exploring every possibility. The Sun, and by extension Earth, orbits the center of the Milky Way at about 220 kilometers per second. This motion is largely determined by the distribution of mass within our orbit, both visible and dark. If there were no dark matter halo, if the Milky Way's mass were concentrated in its visible components, the Sun's orbit would be different. We can use the Sun's observed motion, along with the motions of other stars at various distances from the galactic center, to map the Milky Way's total mass distribution. The result confirms what we've found for other galaxies. Most of the mass is dark matter. It's strange to think that we're swimming through an invisible sea. As Earth orbits the Sun and the Sun orbits the galactic center, we're moving through the dark matter halo at hundreds of kilometers per second. Individual dark matter particles pass through us constantly, billions upon billions of them, each one carrying its tiny bit of mass and momentum, but interacting so weakly that we never notice. This is the hidden context of our existence. Everything visible, everything we can touch and see and measure directly, floats within this vast ocean of dark matter. It's been there throughout Earth's history, throughout the evolution of life, throughout the entire span of human civilization. Our ancestors looked up at the stars and wondered what they were, never suspecting that most of the galaxy was invisible, that the stars they could see represented only a tiny fraction of the Milky Way's mass. Now, in the 21st century, we know better. We can't see the dark matter, but we know it's there. We've measured its effects, mapped its distribution, watched how it shapes galaxy formation and cosmic structure. We've even figured out approximately what it must be like. Massive particles that interact weakly with ordinary matter, forming halos around galaxies, providing the gravitational glue that holds everything together. And yet, for all this knowledge, the fundamental question remains: what is it? What are these particles? Why do they have the properties they do? Why is there 5 times more dark matter than ordinary matter? These questions drive the ongoing research, the experiments deep underground and in space, the theoretical work trying to understand how dark matter fits into the larger picture of particle physics. Take a moment to appreciate the magnitude of what we've learned. In less than a century, we've gone from complete ignorance of dark matter's existence to a detailed understanding of its role in cosmic history. We've mapped its distribution, measured its abundance, predicted its properties. We've incorporated it into a comprehensive model of the universe's evolution from the Big Bang to the present. This is an extraordinary achievement of human curiosity and ingenuity. Let's consider the cosmic microwave background in more detail, because it's such a crucial piece of evidence and such a beautiful example of how the universe's early history is written in light. When the CMB was first detected in 1965 by Arno Penzias and Robert Wilson, it was thought to be almost perfectly uniform, the same temperature in all directions. This made sense if the universe had been very smooth and homogeneous in its early stages. But as measurement techniques improved, tiny variations in the CMB's temperature became visible. These variations are incredibly small, about 1 part in 100,000. In a photograph of the CMB, they show up as slightly warmer and cooler spots. The warmest spots are only about 30 millionths of a degree hotter than the coldest spots, yet these tiny variations contain an enormous amount of information. The pattern of these variations isn't random. There are correlations, relationships between spots at different angular scales. When scientists analyze these correlations, they find that certain scales are preferred. Certain sizes of spots are more common than others. This preference comes from the physics of sound waves in the early universe's plasma. Before recombination, the universe was filled with a plasma of particles and photons. Density variations created pressure variations, which drove sound waves through this plasma. These sound waves oscillated, with regions of compression and rarefaction, until recombination froze the pattern in place. The scales at which these oscillations were strongest when recombination happened left the strongest imprint on the CMB. By measuring this pattern precisely, scientists can determine the universe's composition with remarkable accuracy. The exact mix of ordinary matter, dark matter, and dark energy affects how the sound waves behaved, which in turn affects the pattern we see today. It's like forensic analysis, working backward from the evidence to determine what must have happened. The first peak in the CMB's power spectrum, which measures how strong the variations are at different angular scales, tells us about the total energy density of the universe. The ratio between the first and second peaks tells us about the density of ordinary matter. The third peak is sensitive to the dark matter density. When all these measurements are combined with observations of the large-scale structure and the expansion history, we get a consistent picture. 5% ordinary matter, 27% dark matter, 68% dark energy. These numbers are sometimes called the cosmic recipe. They describe what the universe is made of in terms of energy density, and it's a strange recipe indeed. Most of the universe is invisible, most of the matter is dark, and most of the total energy budget is in the form of dark energy, which behaves unlike anything in our everyday experience. This cosmic recipe has held up remarkably well as new data has come in. Different methods of measuring these components give consistent answers. This is strong evidence that we're on the right track, even if we don't understand all the details. Science often works this way. We recognize patterns, build models that match those patterns, make predictions, and test them. When multiple independent tests confirm the same picture, our confidence grows. As you continue to rest, breathing slowly and evenly, let's think about what all this means for the universe's ultimate fate. We've touched on this before, but it's worth exploring in more detail, because the interplay between dark matter, ordinary matter, and dark energy determines how the story ends. In the early universe, when matter was dense, gravity dominated. The universe's expansion was slowing down. If this had continued, if gravity had remained the dominant force, the expansion might eventually have stopped. All the galaxies, carried by the expansion, might have reached a maximum separation and then begun falling back together, drawn by mutual gravitational attraction. The universe would have contracted, growing hotter and denser until everything merged in a final singularity, a big crunch that mirrored the Big Bang in reverse. But that's not what's happening. Instead, dark energy is accelerating the expansion. As the universe grows larger and matter becomes more diffuse, dark energy's influence becomes ever more dominant. The expansion accelerates faster and faster, carrying distant galaxies away from us at increasing speeds. Eventually, these galaxies will be receding faster than light can travel, which is possible because it's space itself that's expanding, not the galaxies moving through space. When this happens, those galaxies will cross what's called our cosmic event horizon. Beyond this horizon, light emitted by those galaxies will never reach us, no matter how long we wait. The observable universe will shrink, not because anything is physically moving closer, but because the expansion is carrying things away faster than light can catch up. This process will take a very long time. We're talking hundreds of billions of years. But eventually only the local group of galaxies, bound together by their mutual gravity, will be visible to observers in the Milky Way. Everything else will have receded beyond the horizon. The universe will appear to be just our small cluster of galaxies surrounded by darkness. Meanwhile, stars will continue to form, burn and die. But the gas supply is finite. As more gas gets locked up in stars and stellar remnants, less is available for new star formation. The rate of star formation will decline gradually, dropping to zero after trillions of years. At that point, the universe will contain only stellar remnants, white dwarfs, neutron stars, black holes, and planets. These remnants will slowly cool, radiating their heat into space. White dwarfs, which are the cooling cores of dead sun-like stars, will fade from white to red to brown to black over trillions of years. Neutron stars will cool even more slowly, but eventually they too will reach the temperature of the cosmic microwave background, which itself will have cooled to nearly absolute zero as the universe continues expanding. On even longer timescales, quantum processes might begin to matter. There are theoretical reasons to think that protons might be unstable, decaying into lighter particles with an extraordinarily long half-life, perhaps 1035 years or more. If this is true, even white dwarfs and neutron stars will eventually evaporate, as their constituent protons decay one by one over unimaginable spans of time. Black holes will be the longest-lasting objects, but even they aren't eternal. Stephen Hawking showed that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint for large black holes, but it means they gradually lose mass. Eventually, after timescales like 10–100 years for the largest black holes, they will evaporate completely in a final burst of energy. After all this, after timescales so long that they beggar comprehension, the universe will consist of a thin soup of elementary particles and radiation spread across an ever-expanding space. The temperature will be infinitesimally close to absolute zero. Nothing interesting will happen anymore because there won't be enough concentrated energy anywhere to drive any processes. This is the heat death of the universe, the final equilibrium state. It's a bleak picture in some ways. Everything we know, everything we can see is temporary. The stars will go out. Galaxies will fade. Even the matter we're made of might eventually decay. In the longest term, nothing persists. And yet, there's a kind of peace in this knowledge. We exist now in this brief window of cosmic time when the universe is interesting, when stars shine and galaxies cluster and life is possible. We're not at the beginning, not at the end, but in a special epoch when complexity and structure exist, when the universe is rich with possibilities. Perhaps that makes our moment more precious, not less. These are the kinds of thoughts that arise when contemplating the invisible universe and its role in cosmic history. The dark matter that helps structure form, the dark energy that will eventually disperse that structure, the interplay between forces that creates the universe's story from the Big Bang to the far future. But let's return to more immediate concerns. What about alternatives to dark matter and dark energy? Are scientists simply inventing invisible components to patch up their theories, or is there really no other explanation for what we observe? This is a fair question, and it's one that scientists take seriously. The history of science includes many examples of phenomena that seem to require new entities, but were eventually explained by modifying existing theories. Perhaps dark matter and dark energy are like that. Perhaps we don't need new components, we just need better theories of gravity. The main alternative to dark matter is called modified Newtonian dynamics, or MOND. This approach suggests that Newton's law of gravity, and by extension Einstein's general relativity, don't work correctly at very low accelerations. In the outer parts of galaxies, where the gravitational acceleration is extremely weak, perhaps gravity behaves differently than we think, becoming stronger than expected. This could explain why stars in the outskirts of galaxies move faster than predicted without invoking dark matter. MOND has had some successes. It can reproduce the rotation curves of many spiral galaxies quite well, sometimes better than dark matter models. It makes a specific prediction. The relationship between a galaxy's visible mass and its rotation curve should follow a particular pattern, and observations confirm this pattern. Some galaxies seem to have less dark matter than expected, which is puzzling for dark matter models, but fits naturally into MOND. However, MOND faces serious challenges. It has difficulty explaining galaxy clusters, which seem to require more dark matter than even the galaxy's halos would provide. The bullet cluster observation, with its spatial separation between visible matter and gravitational lensing mass, is very hard for MOND to explain, and MOND doesn't naturally explain the cosmic microwave background observations which fit dark matter models so well. Most problematically, MOND is more of a rule than a complete theory. It tells you how to modify gravity, but it doesn't explain why gravity should behave this way. Various attempts have been made to create a complete relativistic theory that includes MOND's effects, but none has been entirely successful. These theories tend to be complex, requiring multiple new fields and parameters, and they often make predictions that conflict with observations. In contrast, dark matter is conceptually simple. It's just matter that doesn't interact electromagnetically. That's a minimal assumption. We already know that matter comes in different types with different interaction properties. Neutrinos, for example, are particles that barely interact with ordinary matter at all. They pass through entire planets without being stopped. Dark matter would be similar, just heavier and interacting even less. The fact that dark matter explains so many different observations, from galactic rotation curves to cluster dynamics, to gravitational lensing, to the CMB, to large-scale structure, is powerful evidence in its favor. It would be quite a coincidence if all these phenomena pointed to the same amount of the same invisible component, unless that component actually existed. Similarly, alternatives to dark energy have been proposed. Maybe the universe's expansion isn't actually accelerating. Maybe we're misinterpreting the supernova data somehow. Maybe we live in an unusual region of the universe, and the apparent acceleration is just a local effect. Maybe gravity behaves differently on cosmological scales. These alternatives have all been investigated carefully. Some can be ruled out definitively. Others remain possibilities but require fine-tuning or special circumstances that seem less natural than simply accepting dark energy's existence. The evidence for acceleration comes from multiple independent sources, supernovae at different distances, the CMB pattern, the growth rate of large-scale structure, the ages of the oldest stars. All of these point to the same conclusion. So while scientists remain open to alternatives, the weight of evidence strongly favors the standard picture. Dark matter and dark energy are real components of the universe. They might not be exactly what we currently think they are. Dark energy might not be a cosmological constant, but something more dynamic. Dark matter might have properties we haven't discovered yet, but something very much like these components must exist to explain what we observe. Let your mind drift gently as you consider these ideas. There's no need to choose sides or reach conclusions. Just observe the evidence, the reasoning, the way scientists work to understand nature. It's a process of careful observation, creative theorizing, rigorous testing, and gradual convergence on truth. Sometimes the truth is strange, involving invisible components and accelerating expansion. But strangeness doesn't make something false. Reality is under no obligation to match our intuitions. Now let's think about how our understanding has evolved over time. The story of dark matter and dark energy isn't one of sudden revelation, but of gradual accumulation of evidence. Zwicky's observations in the 1930s were just the first hint. Vera Rubin's work in the 1970s made the case stronger. Gravitational lensing observations in the 1980s and 1990s provided independent confirmation. The CMB measurements beginning in the 1990s gave us precise numbers. Large-scale structure surveys refined these numbers further. Each piece of evidence built on previous work. Each observation answered some questions and raised new ones. This is how science advances, not in great leaps, but in patient accumulation of knowledge, each generation building on what came before. We stand on the shoulders of giants, seeing farther because of their efforts. The search for dark matter particles is part of this ongoing story. If and when dark matter is detected directly, it will be another piece of the puzzle falling into place. We'll learn what dark matter particles are, how they interact, what their properties are. This will open new avenues of research, new questions to explore. Perhaps dark matter physics will turn out to be rich and complex, with multiple types of dark matter particles forming a dark sector of physics as complex as the ordinary matter sector. Or perhaps direct detection will take much longer than hoped. Perhaps dark matter interacts so weakly that our current technology simply isn't sufficient. That would be frustrating, but it wouldn't invalidate the gravitational evidence. We would know dark matter exists. We just wouldn't know its detailed properties yet. Science can proceed even with incomplete knowledge, gradually filling in gaps as new methods become available. The same is true for dark energy. We might not understand its fundamental nature for decades or even centuries, but we can still study its effects, measure its properties, watch how it influences the universe's evolution. Each observation constrains the possibilities, narrowing down what dark energy could be. Eventually, we'll understand it, even if that day is still far off. There's patience required in science, a willingness to live with uncertainty while steadily working to reduce it. Not every question can be answered immediately. Some mysteries take generations to solve, but the work continues, driven by curiosity and the desire to understand the cosmos we inhabit. As this chapter draws toward its close, let's reflect on what we've covered. We've journeyed from the Big Bang through the formation of the first atoms, the creation of the cosmic microwave background, the dark ages, the formation of the first stars and galaxies. We've seen how dark matter shaped this process, providing the gravitational scaffolding for structure formation. We've watched dark energy gradually assert itself, changing the universe's expansion from decelerating to accelerating. We've explored the evidence from multiple directions: rotation curves, cluster dynamics, gravitational lensing, the CMB, large-scale structure. We've considered alternatives and understood why the standard picture of dark matter and dark energy remains the best explanation. We've looked toward the far future, seeing how these invisible components will determine the universe's ultimate fate. Throughout this journey, we've been guided by observation and careful reasoning. The invisible universe reveals itself not directly, but through its effects. Like detectives gathering clues, scientists have pieced together a picture of cosmic reality that includes far more than what our eyes can see. It's a testament to human ingenuity that we can discover and understand things so far removed from everyday experience. The universe is patient. It unfolds at its own pace, following the laws of physics, shaped by the interplay of matter, energy, space, and time. We are privileged to witness a small part of this unfolding, to understand a fragment of the vast story. The stars above you, the ground beneath you, the air around you, all of it is part of this story. And so are you, made of atoms forged in stars, shaped by billions of years of cosmic evolution, briefly conscious and capable of understanding the universe that created you. Rest now. Let these ideas settle. The invisible universe surrounds you, supports you, shapes everything about your existence. Dark matter holds galaxies together. Dark energy pushes space apart. And here you are in the middle of it all, a small pattern of organized matter briefly capable of contemplating the whole vast sweep of cosmic history. It's remarkable. It's beautiful. It's the universe becoming aware of itself, if only for a moment. In the next chapter, we'll go deeper still, exploring specific mysteries and questions that remain open. We'll look at the cutting edge of current research, the experiments and observations that might finally reveal dark matter's nature. We'll consider what dark energy might be and how scientists are trying to determine whether it's constant or changing. We'll reflect on the limits of knowledge and the joy of exploration, but that's for later. For now, rest, breathe, be present in this moment, floating in the invisible universe, part of the greatest mystery we've ever encountered. Chapter 3. The Mysteries That Remain. Welcome to the final part of our journey together. Take a moment to settle once more into comfort. Feel your body fully supported, your breathing slow and natural. In this chapter, we're going to explore the questions that still puzzle scientists, the mysteries that remain unsolved, and the ongoing quest to understand the invisible universe more completely. We'll move at the same gentle pace we've maintained throughout, allowing each idea to unfold naturally, without urgency or strain. By now, you understand the broad outline of the invisible universe. Dark matter makes up most of the matter in existence, providing gravitational scaffolding for cosmic structure. Dark energy dominates the total energy budget, accelerating the universe's expansion. Together with ordinary matter, they create a cosmos of breathtaking complexity and scale. But understanding the outline is different from understanding the details, and it's in the details where some of the most fascinating questions arise. Let's begin with one of the most fundamental mysteries. What exactly is dark matter made of? We know it exists. We know approximately how much there is. We know it clumps around galaxies and clusters, but we don't know what particles constitute it. This might seem like a technical detail, but it's actually crucial. The properties of dark matter particles determine how dark matter behaves on small scales, which in turn affects the formation of galaxies and the structure of dark matter halos. One possibility we've mentioned is WIMPs, weakly interacting massive particles. These would be particles with mass somewhere between 10 and 1,000 times the mass of a proton, and they would interact via the weak nuclear force and gravity. The weak nuclear force is one of the four fundamental forces of nature, responsible for certain types of radioactive decay. It's incredibly short range, only operating at distances smaller than an atomic nucleus, but it's stronger than gravity. If dark matter consists of WIMPs, they would occasionally interact with ordinary matter through weak force processes. These interactions would be rare, which is why we haven't detected them yet, but not impossibly rare. With sensitive enough detectors and long enough observation times, we should be able to catch them. This is the principle behind direct detection experiments. These experiments are extraordinary achievements of engineering and physics. They're located deep underground to shield them from cosmic rays, which are high-energy particles from space that constantly bombard Earth's surface. Even a mile of rock above the detector doesn't stop everything, so the detectors are built with multiple layers of shielding and sophisticated techniques to distinguish real signals from background noise. The target material in these detectors is usually something very pure and stable. Liquid xenon is popular because xenon is dense, which means more target nuclei in a given volume, and because it can be purified to extreme levels. When a dark matter particle collides with a xenon nucleus, it causes the nucleus to recoil, moving slightly. This motion creates a tiny flash of light and a small electrical signal. By detecting both the light and the charge, scientists can determine the energy of the recoil and distinguish it from background events. But here's the challenge. The expected rate of interactions is incredibly low. A detector containing a ton of xenon might see only a few dark matter events per year if WIMPs exist in the expected range. And even then, you have to distinguish these rare events from other processes that can mimic them. Radioactive decay in trace impurities in the detector materials. Neutrons produced by cosmic ray interactions in the surrounding rock. Random quantum fluctuations in the detector electronics. All of these can create signals that look like dark matter. Distinguishing signal from background requires painstaking analysis. Scientists develop sophisticated statistical methods to separate real events from noise. They look for distinctive patterns. Dark matter interactions should peak in certain seasons as Earth moves through the dark matter halo at different speeds during its orbit. They should have a particular energy spectrum. They should create recoils in a specific way that backgrounds don't. Despite decades of searching with ever more sensitive detectors, no confirmed dark matter signal has been found. This doesn't mean WIMPs don't exist. It just means that if they do exist, they interact even more weakly than some theoretical models predicted. Each null result rules out certain regions of parameter space, certain combinations of mass and interaction strength, narrowing down where WIMPs could be hiding. This process of elimination is actually valuable. Science progresses not just by confirming theories, but by ruling out possibilities. Each experiment that finds nothing tells us something about what dark matter isn't. We're gradually mapping the territory, learning where to look next, refining our understanding of what properties dark matter particles must have. Let yourself relax even more deeply as we continue. Perhaps your eyes are closed. Perhaps you're drifting at the edge of sleep. That's perfectly fine. Let these ideas wash over you like waves on a shore, gentle and rhythmic, requiring no effort to follow. Another candidate for dark matter is the axion. Axions are very different from WIMPs. They would be extremely light particles, millions or even billions of times lighter than an electron. To make up the observed amount of dark matter, there would have to be an enormous number of them, so many that they would behave almost like a wave or a field rather than individual particles. Axions were originally proposed to solve a different problem in particle physics, unrelated to dark matter, but physicists realized that if axions exist with the right properties, they could be dark matter. This kind of connection, where a solution to one problem unexpectedly solves another, is always exciting in physics. It suggests the theory might be on the right track. Detecting axions requires different techniques than detecting WIMPs. Because axions are so light and numerous, you can't realistically detect individual axions. Instead, you look for their collective effects. One promising approach uses strong magnetic fields. In the presence of a magnetic field, axions should occasionally convert into photons, particles of light. The photons would have a specific frequency related to the axion's mass. Experiments like ADMX, the axion dark matter experiment, search for these photons by creating a cavity resonator inside a strong magnetic field. If axions of the right mass pass through, they should produce a detectable signal at a specific frequency. The challenge is that you don't know in advance what the axion's mass is, so you have to scan through many different frequencies, adjusting the resonator each time. It's a slow process, but it's making progress. Other experiments look for different axion signatures. Some search for oscillations in fundamental constants that axions might cause. Others look for effects on quantum sensors or atomic clocks. It's a diverse experimental program, exploring many different possible detection methods. Like the WIMP searches, axion searches haven't yet found a definitive signal, but they're systematically exploring the parameter space, ruling out certain mass ranges and interaction strengths. If axions are dark matter, we'll find them eventually as long as we keep looking in the right ways. There are other dark matter candidates too, sterile neutrinos, which would be heavier cousins of the known neutrinos, primordial black holes, which would be tiny black holes created in the early universe, dark photons, hypothetical particles similar to ordinary photons but interacting differently. Each candidate has its own theoretical motivation and its own detection strategies. The diversity of possibilities might seem frustrating. Wouldn't it be simpler if we knew what we were looking for? But this is actually how science works when exploring truly new territory. You consider multiple hypotheses, test them systematically, and let the evidence guide you toward the truth. Some candidates will be ruled out, others might show promising hints. Eventually, one will be confirmed, and we'll finally know what dark matter is. Now let's turn to dark energy, which is, if anything, even more mysterious than dark matter. With dark matter, we at least have a general framework. It's some kind of massive particle. With dark energy, we're much less certain about even the basic nature of what we're dealing with. The simplest explanation is that dark energy is a cosmological constant, a property of space itself. In this picture, every cubic meter of space contains a fixed amount of energy, what's sometimes called vacuum energy. This energy doesn't dilute as the universe expands, because new space is constantly being created, and each new cubic meter comes with its own vacuum energy. The result is a constant energy density that drives accelerating expansion. Einstein's equations of general relativity allow for such a cosmological constant. In fact, as we discussed earlier, Einstein originally introduced it for different reasons and later regretted it. But if the cosmological constant is real and has a small positive value, it would explain the observed acceleration perfectly. The evidence we have so far is consistent with a constant dark energy that doesn't change over time. But there's a profound mystery here, sometimes called the cosmological constant problem. When physicists try to calculate what the vacuum energy should be based on quantum mechanics, they get an answer that's absurdly wrong. Quantum field theory predicts that empty space should seethe with virtual particles, quantum fluctuations that pop in and out of existence. These fluctuations should contribute to the vacuum energy, and when you add up all their contributions, you get a number that's about 10^120 times larger than what we observe. This is perhaps the worst prediction in the history of physics. It's not even close. It's so far off that it suggests something fundamental is wrong with either our understanding of quantum mechanics or our understanding of gravity, or possibly both. Some mechanism must be cancelling out most of the quantum vacuum energy, leaving only the tiny amount we observe as dark energy, but we don't know what that mechanism is. Various solutions have been proposed. Perhaps there's a symmetry in nature that causes positive and negative contributions to cancel almost perfectly, leaving a small residual. Perhaps quantum gravity effects, which we don't understand yet, change the calculation in crucial ways. Perhaps our universe is just one of many in a multiverse, and we happen to live in one where the cosmological constant is small enough for structure to form and life to exist. In universes where it's larger, galaxies never form, so there's no one to observe it. This last idea, called anthropic reasoning, is controversial. It seems like giving up on finding a fundamental explanation, but it might be the answer, as uncomfortable as that is. The universe might not have a deep reason for its properties. It might just be one possibility among many, selected by the requirement that observers must exist to ask the question. Breathe slowly. Let your shoulders sink. Feel the weight of your body completely supported. These are deep questions, perhaps the deepest in all of science. But there's no need to solve them now. We can simply contemplate them, appreciating their profundity, understanding why they fascinate and perplex the best minds in physics. Another possibility is that dark energy isn't constant. Perhaps it's not vacuum energy, but rather a field, similar in some ways to the electromagnetic field or the Higgs field, but operating at cosmic scales. This hypothetical field is sometimes called quintessence. If quintessence exists, its energy density could change over time as the universe evolves. It might be stronger now than it was in the past, or it might weaken in the future. Distinguishing between a cosmological constant and quintessence requires precise measurements of how dark energy's influence has changed over cosmic history. Scientists do this by studying objects at different distances, which means different times in the past, because light takes time to reach us. If dark energy's strength has changed, this should show up as slight deviations from what a constant would predict. So far, the evidence is consistent with a constant, but the measurements aren't yet precise enough to rule out slow changes. Future observations from telescopes and surveys that will map the universe in unprecedented detail should be able to tell us whether dark energy is truly constant or whether it evolves. This is one of the major goals of observational cosmology in the coming decades. There's also the possibility that dark energy isn't a thing at all, but rather a sign that our theory of gravity breaks down on cosmological scales. Maybe general relativity, which works so well in the solar system and even in binary pulsars, doesn't correctly describe the universe's expansion. Some modified gravity theories can mimic the effects of dark energy without requiring any new form of energy. These theories face challenges similar to Mond's challenges with dark matter. They have to explain not just the acceleration, but also the detailed pattern of the CMB, the growth of structure, and many other observations. So far, no modified gravity theory has successfully explained all the evidence as simply as dark energy does, but research continues, exploring different possibilities, testing them against data. What's remarkable is that we can test these ideas at all. We can observe the universe at different epochs, measure how it has changed, and use that information to constrain theories. A century ago, this would have seemed like science fiction. Now it's routine astronomy, conducted by researchers around the world using data from satellites, ground-based telescopes, and sophisticated computer simulations. Let's consider what future observations might tell us. Several major astronomical projects are underway or planned for the coming years. These will dramatically improve our understanding of dark matter and dark energy, and might finally answer some of the questions we've been discussing. For dark matter, the direct detection experiments continue to improve. Each new generation is more sensitive than the last, able to detect fainter signals and distinguish them from smaller amounts of background. If WIMPs exist anywhere in the plausible parameter range, we should find them within the next decade or two. If not, we'll know to focus our attention on other candidates like axions or lighter particles. Simultaneously, indirect detection efforts are expanding. New telescopes with better sensitivity are scanning the sky for signs of dark matter annihilation or decay. Upgraded particle accelerators might create dark matter particles in collisions, allowing us to study their properties directly. Multiple approaches increase the chances that one will succeed. For dark energy, several large-scale surveys are mapping the distribution of galaxies across cosmic history. The Dark Energy Survey, completed recently, observed hundreds of millions of galaxies. Future projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will observe billions of galaxies over the next decade, creating an unprecedentedly detailed map of the universe's structure. These surveys will measure how structure has grown over time, how the universe's expansion rate has changed, and how dark energy's influence has evolved. They'll use multiple techniques: galaxy clustering, weak gravitational lensing, supernova observations, and baryon acoustic oscillations, which are subtle patterns in galaxy distribution left over from the early universe. By combining all these measurements, scientists will constrain dark energy's properties with extraordinary precision. Space-based telescopes like the Nancy Grace Roman Space Telescope and Euclid will contribute as well, observing from above Earth's atmosphere with exquisite clarity. These missions will study distant galaxies and supernovae, tracing cosmic history back billions of years, watching how the universe evolved under dark energy's influence. Within the next few decades, we should know whether dark energy is constant or changing. We should know its equation of state, a number that describes how its pressure relates to its energy density. This will tell us whether it's truly vacuum energy or something more exotic. And if we're very fortunate, we might discover unexpected phenomena that give us deeper insights into its nature. As you listen, perhaps you're aware of how far we've come in this exploration. From the initial discovery that something invisible was affecting galaxy motions, through the realization that most of the universe is hidden, to the current era of precision measurements and active searches. It's been a journey of expanding knowledge, each answer raising new questions, each mystery inviting deeper investigation. Let's think about some of the smaller scale mysteries, questions that might seem like details, but actually matter quite a bit for our complete understanding. One such question concerns the distribution of dark matter on small scales, in the centers of galaxies and around dwarf galaxies. Computer simulations of dark matter predict that halos should have a particular structure, called a cuspy profile, where the density rises steeply toward the center, but observations of some galaxies suggest their centers have more constant density, what's called a core profile. This discrepancy is known as the cusp core problem. Why does this matter? If it's a real problem, it might tell us something about dark matter's properties. Perhaps dark matter particles interact with each other slightly, which would smooth out the density cusps, or perhaps the process of galaxy formation, with gas falling in and stars forming and exploding as supernovae, redistributes the dark matter in ways simulations don't fully capture. Understanding which explanation is correct will teach us about both dark matter and galaxy formation. Another puzzle involves the number of small satellite galaxies around large galaxies like the Milky Way. Simulations predict there should be hundreds or even thousands of small dark matter halos orbiting the Milky Way, each potentially containing a small dwarf galaxy. But we only observe a few dozen dwarf galaxies. Where are the rest? This is called the missing satellites problem. Several solutions have been proposed. Maybe most of those small halos are too faint to see, containing so few stars that we haven't detected them yet. As telescopes improve, we are indeed finding more ultra-faint dwarf galaxies. Maybe many halos never formed galaxies at all, remaining dark. Or maybe dark matter has properties that suppress the formation of small-scale structure, meaning simulations are over-predicting how many small halos should exist. These questions are being actively investigated. Each new dwarf galaxy discovered, each improved simulation, each better theoretical understanding of how gas behaves in small halos brings us closer to resolving these puzzles. They're not threats to the dark matter paradigm, but they're interesting challenges that will deepen our understanding. There's also the question of whether all dark matter is made of one type of particle or multiple types. Just as ordinary matter consists of many different particles, protons, neutrons, electrons, photons, neutrinos, and more, dark matter might have its own rich particle physics. There could be dark matter atoms, dark matter forces, dark matter radiation. This is sometimes called the dark sector. If a dark sector exists, it would be an entire hidden world of physics operating alongside the familiar world of ordinary matter. Dark matter particles might interact with each other in complex ways, even if they barely interact with us. This could explain some of the small-scale structure puzzles, and it would make the universe even more interesting than we thought. Testing for a dark sector is challenging because, by definition, we can't observe it directly, but we can look for subtle effects. If dark matter particles interact with each other, this should affect how dark matter halos form and behave. Simulations including dark matter self-interactions produce different predictions than standard simulations. By comparing these predictions to observations, we can constrain how much dark matter might be interacting with itself. So far, the evidence suggests that if dark matter self-interactions exist, they're weak. But they're not necessarily zero, and ongoing research continues to explore this possibility. It's a reminder that even when we think we understand something, there might be hidden complexity waiting to be discovered. Let your mind drift with these ideas. Complex possibilities, subtle distinctions, questions within questions. The universe reveals itself slowly, layer by layer. Each answer opens new avenues of inquiry. Each mystery solved exposes new mysteries beneath. This is the nature of deep understanding. It's never final, never complete. There's always more to learn. Now let's consider what the invisible universe tells us about the fundamental nature of reality. One of the most profound realizations is that our everyday experience is not a reliable guide to how the universe actually works. The world we interact with directly involves electromagnetic forces, chemical bonds, solid objects, visible light. This is ordinary matter doing its thing, and it's what we've evolved to perceive and understand. But ordinary matter is rare. Most of the universe operates by different rules. Dark matter doesn't form chemical bonds. It doesn't emit or absorb light. It doesn't make solid objects. It just clumps together gravitationally, forming vast halos that we can't see or touch. And dark energy is even more remote from ordinary experience, a property of space itself that only becomes noticeable on the largest scales. This is humbling. We're built to understand a tiny corner of reality, the 5% that interacts electromagnetically. The rest is alien to us, detectable only through sophisticated instruments and mathematical reasoning. We're like fish trying to understand the ocean, the water, and the world beyond the surface, all at once. We can do it, but it requires going far beyond our immediate sensory experience. This raises philosophical questions about knowledge and perception. How much can we trust our understanding of things we can't directly observe? How do we know we're not missing something even larger than dark matter and dark energy, something so different from our experience that we haven't even thought to look for it? The answer lies in the scientific method: observation, hypothesis, prediction, testing. We might not be able to see dark matter, but we can observe its gravitational effects. We can make predictions about what those effects should look like under different assumptions. We can test those predictions against new observations. When multiple independent lines of evidence all point to the same conclusion, we gain confidence that we're understanding something real, even if we can't perceive it directly. This process has worked remarkably well throughout scientific history. Atoms were hypothesized long before they could be observed directly. Their existence was inferred from chemical reactions, gas behavior, and Brownian motion. Eventually, technology advanced to the point where individual atoms could be imaged, confirming what indirect evidence had already strongly suggested. The same pattern might hold for dark matter: indirect evidence now, direct detection later. But there's always uncertainty. Always the possibility that we're wrong, that some crucial piece of evidence is being misinterpreted, that a completely different explanation will turn out to be correct. Good scientists embrace this uncertainty while still working with the best current theories. It's a delicate balance between confidence and humility, between believing what the evidence says and remaining open to surprises. Take a deep breath. Feel the air filling your lungs, the gentle expansion of your chest. In this simple act, you're engaging with the ordinary matter world, the 5%. Oxygen molecules binding to hemoglobin, energy being released through chemical reactions, electromagnetic forces holding everything together. It's beautiful in its complexity, and it's just a tiny fraction of what exists. Let's explore one more aspect of the invisible universe: its role in the multiverse idea. Some theories in physics suggest that our universe might be just one among many, perhaps even infinitely many. These other universes, if they exist, would be completely separate from ours, with possibly different laws of physics, different fundamental constants, different amounts of dark matter and dark energy. The multiverse idea is controversial. By definition, other universes would be unobservable, at least with current technology and understanding. So how could we ever test such an idea? Some physicists argue that it's not even science if it can't be tested. Others argue that the multiverse is a natural prediction of certain theories, like cosmic inflation, and that we should take it seriously even if we can't directly observe other universes. One argument for the multiverse relates to the cosmological constant problem. If different universes can have different values of the cosmological constant, then it's not surprising that we find ourselves in a universe where it's small enough for structure to form. Universes with much larger values would expand too quickly for galaxies to form. Universes with large negative values would collapse back on themselves too quickly. We exist in this universe because it's one of the rare ones where conditions allow for life. This anthropic argument doesn't explain why the multiverse exists or what determines the range of possible cosmological constants, but it does explain why we observe the particular value we do: selection bias. We can only exist in universes where the value is suitable for life, regardless of whether such universes are common or rare. Similar arguments can be made for other cosmic properties. The strength of fundamental forces, the masses of particles, the amount of dark matter relative to ordinary matter, all of these affect whether a universe can form stars, planets, and life. In a multiverse where these parameters vary, we necessarily find ourselves in one where they're suitable. Regardless of how typical or unusual that combination is, not everyone finds this satisfying. It feels like giving up on finding deeper explanations, but it might be the truth. Nature isn't obligated to provide explanations that satisfy our aesthetic preferences. Sometimes the answer to "why is it this way" is simply because if it weren't, we wouldn't be here to ask. These are deep waters, perhaps the deepest questions we can ask. Why does anything exist at all? Why does it have the properties it does? Are the laws of physics necessary, or could they have been different? Is our universe special, or just one among many? These questions touch on philosophy, metaphysics, and the ultimate nature of reality. Science may never fully answer them. Some questions might be beyond the reach of empirical investigation, but we can still make progress, still narrow down possibilities, still deepen our understanding even if complete answers remain elusive. And there's value in the questions themselves, in the contemplation they invite, in the way they stretch our thinking beyond the everyday. Let yourself sink deeper into relaxation, your breathing slow and steady, your body at rest. The mysteries we've discussed are vast, but they don't require your active engagement. Just let them be, existing in your awareness like distant stars, beautiful and unreachable, inspiring wonder without demanding comprehension. As we approach the end of our journey, let's reflect on what it means to live with mystery. In earlier eras, unexplained phenomena were often attributed to gods or magic or forces beyond human understanding. Science has systematically replaced these explanations with natural ones, showing that the universe operates by consistent, discoverable laws. Thunder isn't Zeus's anger, it's electricity in the atmosphere. Disease isn't divine punishment, it's germs and genetics. The sun doesn't move across the sky, the earth rotates. But solving old mysteries has revealed new ones. We understand electricity, but now we puzzle over dark energy. We understand atoms, but now we search for dark matter. Each answer expands the boundary of our knowledge, bringing us into contact with new unknowns. In this sense, mystery is permanent. The universe is endlessly complex, and we'll always be discovering new things we don't understand. This is cause for celebration, not despair. A completely understood universe would be boring. There would be nothing left to discover, no questions left to ask. The existence of deep mysteries, like the nature of dark matter and dark energy, means the adventure continues. Each generation gets to participate in humanity's ongoing quest to understand reality, and each makes its own contributions to that understanding. You're part of this story. By learning about the invisible universe, by contemplating these mysteries, by allowing yourself to wonder, you're engaging with some of the deepest questions humans have ever asked. You don't need to solve them. Just being curious, just caring enough to listen and learn, connects you to the grand tradition of human inquiry that stretches back thousands of years and will continue long into the future. The invisible universe also teaches us about limits. We're finite beings with finite lifespans and finite capacity to understand. We live in a particular time and place, with access to certain technologies and certain levels of knowledge. Future generations will know more than us, just as we know more than past generations. But they too will have limits, will face mysteries that challenge their understanding. This is the human condition. We reach for comprehension, make real progress, yet never achieve complete understanding. There's always another layer, another question, another mystery, and that's okay. The journey is valuable in itself, regardless of whether we ever reach a final destination. Perhaps dark matter will be detected in your lifetime. Perhaps dark energy's nature will be revealed. Perhaps entirely new phenomena will be discovered that we haven't even imagined yet. Or perhaps these mysteries will persist for generations, challenges for your children and grandchildren to grapple with. Either way, the quest continues. The invisible universe remains, patient and persistent, waiting to reveal its secrets to those curious enough to look. Let's think about the emotional and psychological aspects of living with cosmic mystery. Some people find it unsettling to know that most of the universe is invisible, that our understanding is incomplete, that reality is stranger than it appears. They might prefer a simpler world, one where everything is what it seems, where there are no hidden depths. But there's another response: wonder. The invisible universe is amazing precisely because it's invisible. It challenges us to think beyond our senses, to use reason and creativity to understand what we cannot directly perceive. It reveals that reality is richer and more complex than our everyday experience suggests. This is awe-inspiring, a source of profound beauty and fascination. Throughout history, humans have sought wonder and mystery. We tell stories of hidden worlds, magical realms, dimensions beyond our own. In a sense, the invisible universe is all of these things. It's a hidden world that actually exists, more wondrous than most fiction because it's real. Dark matter and dark energy aren't magic, but they're extraordinary. They reshape our understanding of everything. Embracing this wonder, allowing yourself to be amazed by what we've discovered and humbled by what we don't know, enriches life. It provides perspective on our daily concerns, reminding us that we're part of something vast and mysterious. It connects us to the cosmos, to the billions of years of history that preceded us, and to the unknowable future that stretches ahead. Your existence itself is remarkable. You're a temporary pattern of atoms, organized in ways that allow consciousness, thought, and feeling. Those atoms were forged in stars billions of years ago, scattered through space when those stars died, eventually incorporated into the planet you live on and the body you inhabit. The dark matter halo surrounding the Milky Way held everything together gravitationally, allowing the galaxy to form and persist long enough for this to happen. In this sense, you're connected to the invisible universe. You couldn't exist without it. The galaxies that formed in dark matter halos, the stars that coalesced from gas pulled together by dark matter's gravity, the planets that formed around those stars, all of this depended on dark matter. And dark energy, by determining the universe's expansion rate and ultimate fate, sets the context for everything. You're not separate from the cosmos, observing it from outside. You're part of it, made of it, shaped by it. The invisible universe isn't something distant and abstract. It's the foundation upon which everything you know exists. Understanding this deepens your connection to reality, making you aware of the vast web of relationships that connect everything to everything else. Breathe in this awareness. Let it settle into your consciousness. You're floating in an invisible ocean, supported by forces you cannot see, shaped by processes that operated long before you were born and will continue long after you're gone. This is both humbling and elevating. You're small, yes, but you're also part of something infinite and eternal. As we near the end of this chapter and this journey, let's consider what comes next for humanity's understanding of the universe. We've made extraordinary progress in the past century, discovering that the universe is expanding, that it began with the Big Bang, that it's mostly invisible. We've mapped cosmic structure, measured the universe's composition, traced its history from the first moments to the present, but we're still in the early stages of truly understanding reality. Dark matter and dark energy are just the beginning. There are deeper questions. How do quantum mechanics and gravity fit together? What happened before the Big Bang, if anything? Is our universe unique or one among many? What is consciousness and how does it emerge from physical processes? These questions might take centuries to answer, or they might remain permanently beyond our grasp. Yet the quest continues. Each generation builds on the work of those before, adding new pieces to the puzzle, developing new technologies, asking new questions. You're living in a remarkable time, when the invisible universe is being actively explored, when experiments might soon detect dark matter, when telescopes are revealing cosmic history in unprecedented detail. Stay curious. Keep learning. Allow yourself to wonder. The universe is offering you the greatest mystery story ever told, and you have the privilege of watching it unfold. New discoveries will be made. New mysteries will emerge. The adventure never ends. The invisible universe is all around you right now. Dark matter streaming through your body, dark energy pushing space apart at the largest scales, quantum fields permeating every point in space, gravitational waves rippling through space-time, all invisible, all real, all part of the magnificent tapestry of existence. You don't need to understand all the details. You don't need to solve the equations or master the physics. Just knowing that this hidden reality exists, appreciating its mystery and beauty, connecting with the sense of wonder it inspires, this is enough. This is the gift the universe offers to anyone willing to look beyond the surface, to question, to explore, to remain open to surprise. Let's end our journey with a moment of quiet reflection. You've traveled far in these hours, from the Big Bang to the present, from visible matter to dark matter to dark energy, from what we know to what remains. Mysterious, you've glimpsed the vast architecture of cosmic time, the hidden structure underlying everything you can see. Take a final deep breath. Feel gratitude for the scientists and thinkers who've worked to understand all this, who've dedicated their lives to mapping the invisible universe. Feel connection to everyone else who's pondered these mysteries, who's looked up at the stars and wondered what else might be out there. Feel peace in knowing that you're part of something larger than yourself, something ancient and ongoing and fundamentally mysterious. The universe doesn't have all the answers, and neither do we. But we have questions, curiosity, the capacity to learn and wonder. We have each other, sharing this journey of discovery across generations. We have the cosmos itself, patiently revealing its secrets to those who take the time to look and listen. The invisible universe remains as it always has, surrounding you, supporting you, shaping your existence in ways both subtle and profound. You can't see it, but it's there. You can't touch it, but it touches everything. You can't fully understand it, but you can appreciate it, wonder at it, feel connected to it. And perhaps in some small way, through your curiosity and attention, through your willingness to learn and think about these deep questions, you're participating in the universe's process of understanding itself. You're a part of the cosmos that has become conscious, that can reflect on the whole, that can ask why and how and what comes next. This is remarkable. This is beautiful. This is the gift of consciousness, of being alive at this particular moment in cosmic history. You're witnessing an era of discovery, living in a universe that's mostly invisible, but slowly revealing itself to those patient enough to observe, creative enough to theorize, and humble enough to accept that reality might be stranger than we ever imagined. Rest now. Let sleep come if it will. Let these ideas drift through your mind like stars across the night sky, beautiful and distant, inspiring without demanding. The invisible universe will still be there when you wake, patient and persistent, filled with mysteries waiting to be explored. You've completed this journey. You've learned about what lies in the unseen universe, but the real journey never ends. Every time you look up at the stars, remember, what you see is only 5%. The rest is hidden, invisible, waiting for us to understand it. And that's wonderful. That's perfect. That's exactly as it should be. Sleep well. Dream deeply. You're floating in the invisible universe, held by dark matter's gentle gravity, pushed by dark energy's patient expansion, surrounded by mysteries that make existence worthwhile. You're part of it all, and it's part of you, and the story continues forever, with new chapters being written every moment. In stars too distant to see and particles too small to detect, in the vast spaces between galaxies, and in the quantum foam of space-time itself, the universe is magnificent. The invisible universe is perhaps even more magnificent, and you, by taking the time to learn about it, have joined the ancient human tradition of seeking to understand the cosmos we inhabit. That's enough. That's everything. Rest now, and when you wake, the universe will still be there, still mysterious, still beautiful, still waiting to reveal more of its secrets to anyone curious enough to listen.